Hello. Today we'll be taking a look at this physics problem. It is a projectile motion problem related to the kinematics unit. I'm going to read through the problem, we're going to map it out, and then we're going to solve through all of the questions together. So, a cannonball is fired at an initial velocity of 40 meters per second at an angle of 45 degrees above the horizontal. We want to determine the total time of flight. So the total time it takes for the ball to complete its motion from the time it's fired to the time it hits the ground. Next, we want to calculate the maximum height reached by the projectile. So I'll call this our displacement in the y max. Next, find the horizontal distance or the range of the projectile. So that'll be our displacement in the x. And then finally, what is the velocity of the projectile 2 seconds after it's fired? So we'll look at this a little bit more in detail once we get there, but we can for now just consider this as some velocity or final velocity at 2 seconds. Okay? So, as always, let's set up our compass. I'm going to state that north and east are our positive directions, and south and west are our negative directions. So we've got some cannon, right, that's gonna fire our ball here at 40 meters per second. So I'm gonna draw a really quick diagram just to better visualize what's going on. So our ball is being launched at an angle of 45 degrees above the horizontal, and that velocity, right, is 40 meters per second, and the ball is launched. It's going to follow a path somewhat similar to this and eventually hit the ground somewhere here. So it's being launched off of the ground and then eventually coming back to the ground. So I'm going to write down what I know. I know that our initial velocity is 40 meters per second, and that's east 45 degrees north. This, right, can be broken down into its two components, its x and y component. So I can say Vix equals and Viy equals. And when we're doing problems like this, it is an expectation that we have a good understanding of how to utilize our trigonometric ratios. So if I take, right, this kind of vector here, that's 40 meters per second, I get an angle of 45 degrees. Right, my angle of interest here being 45 degrees, if I want to find my x, which is this side, I got to be able to solve for this side. So this is my adjacent side with respect to that angle. So I'm going to use cos, right? And upon rearranging, I'm not going to show that work here. Again, the expectation is that we understand how to utilize our trigonometric ratios by the time we get to our physics unit. So I'm going to specify that my initial velocity in the x component is 40 cos 45 degrees. And then for my y component, it's going to be the opposite side, so that'll be 40 sine 45 degrees. Which actually, we will end up just getting the same value for both our x and y components because of that 45 degree angle, that special angle there. But anyways, we also know that we're going to have some gravitational acceleration, so that impacts the acceleration in our y component, and unless otherwise specified, it's always going to be 9.8 meters per second squared in the south direction or downwards direction. And there's one other thing that I can take away from this, right? I know that my ball is being launched from the ground and it's eventually landing back on the ground. Unlike other examples where the ball might land on an elevated surface, or it might be launched off of a cliff and then land below the cliff, right? In this case, it's being launched from our ground and then, right, landing back on that same kind of reference point where our ground is. So I can therefore specify that my displacement in the y is actually 0 meters. So that'll be some useful information for us when we go to solve the rest of our problem. Okay? So now we got everything set up. Let's now solve the first problem. Determine the total time of flight. Okay? So I want to find that time, and I'm going to utilize the components I have from the y dimension to help me solve for that. So I'm going to say that my displacement in the y is equal to my initial velocity in the y times time plus 1/2 times the acceleration in the y times time squared. So utilizing one of my big 5 equations here, understanding, right, that I have a displacement, I have a velocity, initial velocity, I have an acceleration, and I want to solve for the time. So I've got 3 of the 4 unknown values, 4th being the time, and I can plug in my known values to then solve for that missing value. So my displacement, 0, equals my initial velocity. I'm just going to plug it in like this for calculation purposes. So I'll put 40 sine 45 degrees times time plus 1/2 times negative, right? It's a negative value because based on my compass, south or down is in the negative direction. So that'll be negative 9.8 times my time squared. So I've got some quadratic formula here now. I'll further simplify it to get 28.28 times my time plus, or actually it'll be negative now, 1/2 times negative 9.8, so negative 4.9 times squared. So I could either rearrange this using some algebra or utilizing my quadratic formula. I'm going to solve this using the quadratic formula, right? My a value is going to be negative 4.9, my b value is going to be 28.28, and my c value is just going to be 0. I'm not going to show the whole step-by-step process of how to use our quadratic formula here, but after I calculate that, I'm going to get a time of 0 or a time of approximately 5.77 seconds. Now I know that it's not going to be 0, right? That's kind of exactly where my initial point is. I care about the total flight time, so I'm therefore going to utilize this 5.77 seconds, right? So that'll be my answer for part A. Okay, so now for part B, we want to calculate the maximum height the projectile or the ball reaches. So that's going to be this height here. So this approximate maximum height in which the ball reaches after being launched. And so to find that, there is a key piece of information we need to know when dealing with any projectile motion problem, and it's that at the maximum height, we have to assume that that velocity right here in the y component or the y dimension is going to be equal to 0. So the Vy at the max height is going to be equal to 0 meters per second. It's just at that point transitioning from a positive velocity in the y to now a negative velocity in the y, okay? That's why at that instant, we consider that Vy max at that max height to be 0. So I can therefore utilize my initial velocity in the y as 28.28 meters per second, which is just this here, right? And then instead of writing it as Vy max, I can basically evaluate here this as like my point 1 and this being my point 2, so my initial, my final position, and say that my velocity, final velocity y there is going to be 0. And then as always I'll use my acceleration in the y, which is 9.8 meters per second squared. Down, this is going to be north, by the way, upwards. Okay, so I've got these three values that I can utilize to solve for what I classified here as my max height. Okay, I can use the following big 5 kinematics equation. My final velocity squared equals my initial velocity squared plus 2 times my acceleration times my displacement. Okay, I'll plug in my values. My final velocity, like I said here, is 0. So 0 equals my initial velocity squared, which will be 28 squared plus 2 times the acceleration, which is negative 9.8 times that displacement. And I'll call this, again, our dy. This here is represented by our dy max. So I'm going to have 28.28 squared, which gives me 800 minus 2 times 9.8, which gives me 19.6 times the displacement. I'm going to rearrange and then solve for that displacement, so I'll have negative 800 equals negative 19.6 times the displacement. Divide both sides by negative 19.6. And that'll give me a final displacement of approximately 40.82 meters, which represents that maximum height. Okay, so therefore the maximum height reached by the projectile or the ball is 40.82 meters. Next, part C, I want to figure out that horizontal distance that the ball reaches. So the distance between here to here. Okay, so what I'm going to do is I can utilize my velocity x equals displacement in the x over my time equation. Because I know that my velocity in the x component is consistent, right? It's not changing because I'm not experiencing any acceleration in the x dimension. We can assume that the velocity in the x dimension remains the same. And we can also derive this using one of our big 5 equations as well, right? Because of that acceleration being 0. Just a side note to quickly show you how that works is if I have my displacement in the x, let's use that same equation we used from part A, my initial velocity times my time plus 1/2 times my acceleration times time squared. Because I have no acceleration in the x dimension, this whole term goes to 0, right? So I'll just be left with this, which when we rearrange this, it's the exact same thing. If I multiply both sides by time here, I'm going to have displacement equals velocity times time. Okay, so I'll utilize this and state that our displacement in the x is equal to our initial velocity, which is 40 cos 45 times the time, which we got as 5.77. And when I put that in my calculator, I'm going to get a range or a displacement in the x of approximately 163.2 meters in the eastwards direction. And again, just to clarify, that initial velocity that I'm using, right, it remains the velocity at the initial state, throughout the middle, at the end, right, because there's no acceleration changing that initial velocity. That's why we can assume that it stays the same throughout the whole motion. That's why we can utilize it as what's considered as our average velocity throughout the entire motion. So the horizontal distance of the projectile or the ball is 163 meters in the eastwards direction. Finally, for the last part of this problem, we want to find the velocity of the projectile 2 seconds after it's fired. Okay? So we know the total time that the ball is in the air is about 5.77 seconds. So let's just assume, we don't know, it doesn't matter exactly where it is, but let's just say the ball is somewhere here. Okay? 2 seconds after its launch. We essentially want to find that entire velocity vector at this point, 2 seconds after it's fired. So, like I mentioned in part C, the velocity in the x is going to be the same throughout the entire motion. We'll first have to find the velocity in the y. So very important that we find both components of our velocity at this 2 second point. Once we find the two components, we can then utilize the Pythagorean theorem to find the vector, so the actual vector, with its direction. So we'll solve for the angle as well to get that final velocity, or the velocity at this 2 second point, right? So I'm going to specify that the velocity in the x that I'm going to utilize is just 40 cos 45 degrees, which gives us about 28.28 meters per second. My velocity in the y, I don't quite know that, right? So I'm going to solve for that, but let me specify as well that our time is going to be equal to 2 seconds, right? And then everything else will be the same for the most part. We also got this acceleration that we'll utilize as well. So let's say that this is our new VF for this question. I'm going to utilize this as my final state and the launch time as my initial state. So in order to find that final velocity, I'm going to specify that my final velocity, right, this is the big 5 kinematics equation that I'm going to use. My final velocity of the y there is equal to my initial velocity of the y plus the acceleration of my y times the time. And when I plug in all my values, I'm going to get my final velocity in the y is equal to, also the same thing as here, it'll be, right, 40 sine 45, which also gives me 28.28, and again that's because 45 degrees is a special angle. So 28.28 plus my acceleration, which is negative 9.8, times my time, which I've given at 2 seconds, where I want to evaluate that. And when I punch that in my calculator, I'm going to get a final velocity in my y at that 2 second point of approximately 8.68 meters per second, and it's positive, so it'll be in the northwards direction. So now that I've got my Vx, my velocity in the x, and my velocity in the y, I can now draw out these two vectors to kind of get a better understanding of what's going on here. So this is my v of x, and this will be my v of y. Okay? And so the resultant vector, which will be my final velocity, is going to be this here. This will be my velocity at 2 seconds. Okay? So let's utilize Pythagorean theorem. C squared equals a squared plus b squared. So I can just state that my velocity squared, right, this hypotenuse here, is going to be equal to vx squared plus vy squared. So then I'll have v squared equals 28.28 squared plus vy, which is 8.68 squared. And then when I rearrange everything and square both sides, I'm going to get a final velocity of approximately 29.58 meters per second. So that'll be the value of that, but I still want to figure out this angle to give that velocity vector its direction. So I'm going to utilize my trigonometric ratios again. I could use either one because I have the value for every side, but I'm just going to say that I'm going to use tan and say that tan theta equals my opposite side over my adjacent side. And again, just to kind of note here, it's very important I got a good understanding of my trig ratios, including how to use the Pythagorean theorem before solving any projectile motion or physics related problem. So I'll have my tan theta equals my opposite side, which will be Vy over my Vx. And then I'll need to take the inverse tan, right? Which will look like this, with my Vy, which is 8.68, over my Vx, which is 28.28. When I punch out in my calculator, I get an angle of about 17 degrees. Alright, so therefore, the velocity of the projectile 2 seconds after it's fired is going to be 29.58 meters per second east, 17 degrees north. Okay? So a really good projectile motion problem here. Do try and practice some of these on your own. If you guys got any comments or questions, please let me know. And as always, I hope this video helped.